In the previous videos, we have done the derivation of the partition function for various examples of quantum of canonical ensembles. And today we will try to derive the partition function for a real world system, which you might have done your experiments even and measured the parameters, which is a magnetic system. So we are dealing with a paramagnetic system. So what is a paramagnetic system? Paramagnetic system is those kind of magnetic systems which have got a effective magnetic moment and which get magnetized in the presence of a magnet, of an external magnet, but their magnetic moment is much lesser compared to a ferromagnet. So that is the simplest and the smallest way in which one can talk about a paramagnetic system. So here, this paramagnetic system can also be considered as an example for a canonical ensemble. Here, because as you apply the magnetic field, you have the interaction between the magnetic moment and the magnetic field, which leads to evolution in its occupied energy levels. So since there's a difference in their energies, we always consider that into categorize them into canonical ensemble. So here, for the purpose of derivation, we consider a spin half system. Okay, which means that you have spin half particles, for example electrons, right? And that is kept in a magnetic field, right? So here the kinetic energy does not come into picture. Instead, it is the potential energy which is effectively coming into picture. So how do you define the magnetic moment, the potential energy of a magnetic system? You might have learned, I don't know, I'm not sure of that. The potential energy is normally defined by minus mu dot B, where B is the magnetic field and mu is the magnetic moment, right? So minus mu dot B, or you can write it as minus mu B cos theta, right? So this is how you will define the potential energy of a magnetic system, which means that we can represent it like this. So here is a system, and then you apply a magnetic field, and then the system will get possess the energy levels which are which originate because of the magnetic field, and you have two levels coming into picture. One with the upspin, those particles which do align with the magnetic field, and those particles which align opposite to the magnetic field. So this is 0 degree, this is 180 degree, and here I have the energy minus mu B, and this here I will have the energy plus mu B, right? Minus mu B and plus mu B. We can write the expression according to that then. So the partition function Qn is equal to sum over e raised to minus beta e, right? Qn is equal to sum over e raised to minus beta e. So here we have two different energy levels, and the energies are mu b and minus mu b and plus mu b. So we substitute that over there, and then we can write it as e raised to minus beta mu b plus e raised to minus beta minus mu b is equal to e raised to minus beta mu b plus e raised to mu beta b, right? So this is this is our partition function. But if we want to simplify that, we can write it as using the expression for cos hx. What is that telling? Cos hx is equal to e raised to minus x plus e raised to x divided by 2. So this is the general expression for cos hx. So we can substitute that, we can apply this kind of identity over here, and then we can write it as q can be re-expressed as 2 cos h beta mu b, right? 2. So this is 2 cos h beta mu b. So this is the expression for the partition function for a paramagnetic system. And of course, you can go on to calculate the free energies, Helmholtz free energy, for example. So it is minus kT ln q is equal to minus kT ln 2 cos h beta mu b, right? And u is equal to what? Minus dou by dou beta of ln q, right? I can write that expression as u is equal to minus dou by dou beta ln of 2 cos h beta mu b, right? Which can be written as you can do the differentiation here, and we will write we can write this as, you can check yourself, minus 1 into 2 sin h beta mu b divided by 2 cos h beta mu b, right, into mu b. Therefore, that can be written as minus mu b tan h beta mu b. So this is the expression for the average magnetic energy of a paramagnet in the statistical mechanical way. This you will see this is a similar expression when you next semester when you learn the solid state physics about the paramagnetic section. In the paramagnetic section, there also you might get into this derivation, and maybe not derivation. There we will use it straight away, right? But there you will have more things to do with this formula. So be ready to use it there. But there you will, but the fundamental equation we need there is mu b tan h beta mu b. Now within this equation, let me ask you, what will happen if T tends to infinity, which means that what will happen if at very high temperature, right? Yeah, very high temperature, one of the implications is that the beta, what is beta? Beta is equal to 1 by kT, right? So therefore beta will tends to 0, right? Beta tends to 0, which means that if I apply that in this expression for the u, beta tends to 0 means I will get into a situation of u tends to 0, right? Because the tan h 0 is 0, and if beta is tending to 0, which means that my u will tend to now the 0. So which means that at very high temperature, my average magnetic energy tends to 0. This is one inference out of that expression for u. Now let me ask you, what is the expression tends for magnetization? So magnetization M can be expressed in terms of A minus dou A by dou B at constant temperature, of course, minus dou A by dou B is equal to KT dou by dou B of ln 2 cos h beta mu b, right? This is dou by dou b. Okay. So if I do that derivation, that differentiation, I will get KT 2 sin h mu beta b divided by 2 cos h mu beta b into mu b, which will come to be mu tan h beta mu b. So that is the expression for the magnetization, right? So of course you have the connection between the u and the m, which is m by u. If I take it, then so if I take this as equation 3 and this is equation 4, that means equation 3 by equation 4 will give me m by u is equal to minus 1 by b, which means that u is equal to minus mb for a paramagnetic system based on my expression. So in the problem, in the university problem, sometimes it may be to prove this point, u is equal to minus mb for a paramagnetic system based on the canonical ensemble, then this is a way to do something like that. And there could be various other kind of variations of these kind of expressions which one should be aware of. Okay, so that's it. So that is a partition function for a paramagnetic system and its inferences and consequences of that expression. Okay, so that is it.